In the last section, we started talking about galvanic cells or voltaic cells, but what we said was we're going to have two reactions. One side is going to be an oxidation reaction, the other side is going to be a reduction reaction. I'm going to connect my two reactions with a wire so that electrons can flow, so I get current flowing. And I'm going to connect them with a salt bridge or a porous disc so that I can balance charges so that the voltaic cell keeps going. Now, I said that the voltage, the electrical current, is going to be measured by a voltmeter. And so I'm going to be able to determine how much current is actually being produced. Now, when I talk about how much current is being produced, I can either talk about it qualitatively or quantitatively. If I look at my activity series, the further apart two different elements are, the more voltage is going to be produced. So if I have two elements, for example, calcium and sodium, calcium's higher, it's going to be oxidized. Sodium's lower, it's going to be reduced. Because they're very close together, I'm only going to create a little bit of voltage. If I made a voltaic cell with calcium, and let's say we go all the way down here to copper, I'm going to produce much, much more electric current because my calcium is much better at getting rid of the electrons than copper. And so I'm going to have a lot more electrons moving, more current. I can also calculate my potential quantitatively. Now, remember, whenever I see this little degrees sign, this is telling me that it is in standard conditions. Standard conditions are 1 atm of pressure and 25 degrees Celsius. Now there are two ways I can calculate how much voltage my cell is producing. I can either take how much electricity or the potential my cathode will produce and subtract my anode. Remember, my cathode is being reduced. My anode is being oxidized. Or I can take the potential for the reduction and add the potential for the oxidation. Now, here's what that actually looks like. I'm given a table for how much standard reduction potential, different half reactions produce. These are, again, standard. Okay? I can only say that the standard for my cell is equal to what I actually have if it's at 1 atm and 25 degrees Celsius. If it's not, these two things aren't the same. Okay? Now, here's the way it works. If I look at the table, these are all how much current will be produced if my element is being reduced. Okay? I want it to be positive. The more positive it is, the more easily it is reduced. So if I look, fluorine, very, very electronegative, it really wants to gain those two electrons to be reduced. Very big positive value. Okay? If I look down at lithium, lithium wants to give up electrons a lot. It's very easily oxidized. So the reduction potential is very negative. If it's positive, it wants to be reduced. If it's very negative, it wants to be oxidized. Okay? So these are reduction potentials. If I want to figure out how much energy is produced if it's oxidized, I need to change the sign. So in order for lithium to be reduced, it would have to absorb 3.05 volts. If lithium is oxidized, it will lose 3.05 volts. okay? Now, if I change the coefficient of my half reaction, it does not affect the value, okay? So if I have one lithium atom being reduced, it needs to absorb negative 3.05 volts. If I have 2, still 3.05 volts. 3, still 3.05 volts. It doesn't matter what the coefficient is, this value does not change, okay? So here I've got my galvanic cell, or my voltaic cell. I've got zinc. Here is the solid. The solid is being oxidized. It is losing electrons. As it loses electrons, my solid zinc is turning into zinc 2+, and it joins the rest of my aqueous ions. So over time, this metal is actually getting smaller, okay? So zinc is being oxidized. It is my anode. Electrons are flowing towards copper. Copper is my cathode. It is being reduced. So as it gains electrons, what happens is my copper 2+ in solution is going to become copper metal. So my zinc solid is going to get smaller as the metal turns into zinc 2+. My copper solid is going to get bigger as the 2+ turns into solid. And then I have my porous disk so that my positive ions and my negative ions can balance out so my reaction keeps going. Okay? So let's say I wanted to figure out how much voltage was produced in this reaction. Okay? I can do this one of two ways. I look at my values. So I look here. Remember, these are reduction potentials. So the one that is more positive is going to be reduced. It is going to be the cathode. Okay? So then what I'm going to do is I am going to reverse the half reaction that is less positive, and I'm going to add it to the reduction half reaction. This will allow me to calculate the E for my cell. Okay? So here's the way I would do this. If I look at my table, I've got zinc and copper. So I look at my table, zinc's here. I would find copper. Copper's not actually on this table, which is a pain. Nope, not even on this table, it's so far down. Oh, wait, there it is. Copper, okay? Now, if I look at this, copper is 0.16, zinc is negative 0.76. Because copper has 0.16, it is more positive. It is going to be my cathode. Okay? So I've got 0.16. I've got zinc. Zinc is negative. It would be my anode. Because it is my anode, I change the sign. So that would be plus 0.776. I would add those together. My galvanic cell is going to produce 0.92 volts. It does not matter if my reaction is balanced. I don't need to change coefficients. It works out exactly the same. Okay? So take a second and look at example 5. I've got my galvanic cell, aluminum 3+ and Mg solid is going to make aluminum solid and Mg 2+. They give you the two half reactions, and they give you the voltage. Now they want you to do two things. First, balance it. So right now, our electrons aren't balanced it. So balance the reaction so that the electrons are balanced. Once you've done that and you have your balanced chemical reaction, calculate the E cell. So remember, the more positive is going to be the cathode. The more negative is going to be the anode, so I need to change the sign, and then I add them together. It does not matter what the coefficients are. So again, I've got another galvanic or voltaic cell. It gives me my two half reactions. It gives me the voltage for each half reaction. I want to do the balanced cell, and I want to calculate how much. Well, if I look, I've got 1.51, 1.19. This is more positive, so it is going to be my cathode. Even though this is a positive value, it's a smaller positive value, it will be my anode, which means I need to change the sign. Okay? So if I add those two together, plus 1.51 minus 1.19, I get my overall voltage for the cell is a positive 0.32 volts. If I wanted to balance my reaction, right now, 5 electrons and 2 electrons. I would multiply this by 2. I would multiply this by 5. Now I'm not just multiplying, I'm also flipping the second one. So this is actually backwards. So I'm going to write this down here. I've got 2 MnO4 negative plus 10 electrons plus 16H plus forms 2 Mn2 plus 2 times 4 is 8 H2O. Okay. If I was looking at this one, remember I flipped it, so I'm going to have 5 times ClO3 negative. I'm going to have 5 times H2O. That's everything on this side. On the other side, I'm going to have 5 ClO4 negative, 10 H plus, and 10 electrons. Anything that's the same on both sides, I cancel out. 10 and 10 are gone. I have 16 hydrogens, 10 hydrogens, so all of these are gone. I'm left with 6. 8 waters here, 5 waters here. All 5 go away. I'm left with 3. So when I write my complete balanced reaction, I'm going to have 2 MnO4 negative. I'm going to have 6 H plus, 5 ClO3 negative, 5 ClO4 negative. I'm going to have Mn2 plus times 2, and I'm going to have 3 H2Os. So this is my complete balanced reaction. Okay? So when I calculate the cell, it doesn't matter that I've got 2 of those or 6 of those or 5 of those. Don't care. I just take the positive one, less positive one, change the sign, and add them together. Okay? My cell will always run spontaneously if I get a positive value. If you do not get a positive value, you have things set up backwards, okay? Make sure you look this over and you can calculate your standard cell potential for your voltaic cell.